Hello, my name is Joanne Scott. I'm the Executive Director of the 3MF Consortium. And today we have Erik Denlinger from PanOptimization to talk about their build, simulation, and optimization software. If anyone has any questions, please put them in the Q&A, not in the chat, and we'll address them at the end of the presentation. Erik, do you want to take it away?
Yeah, thanks, Dwan. So like Dwan said, I'm Erik Denlinger. I was co-founder of PanOptimization. Before I get started, I do want to thank you, Dwan, for inviting us to present here and for doing a good job marketing the event. So we really do appreciate it. The scope of the presentation here is really just going to be an overview on the technology that we are developing and licensing at PanOptimization. And it's maybe 10 or 12 slides. It's going to be fairly technical in nature, so I'm going to try to go through them at a pace. Each one kind of builds on the previous. So I'm going to try to go through them at a pace where I don't lose anybody. So before I get into the technical, just a little bit on our background. PanOptimization was founded in 2022 by Pan Michaelaris. Pan had previously been a professor at Penn State for 20 years. And he also previously founded Pan Computing, which had the first commercial product for FEA simulation of additive manufacturing. So you may be familiar with we have a few books out and some book chapters and handbooks for some of our previous software work. Where I really want to start the presentation here is with the question of why did we start PanOptimization? It's an awful lot of work. So why do it? And in our opinion, the additive market has a lot of unmet simulation and optimization needs. So the name of the company, PanOptimization, is because the original idea that excited us to start the company is we wanted to look at solving gradient-based optimization problems for additive. We saw that there really wasn't a lot of activity in the optimization space for design and build prep in additive, and we thought that seemed like a good opportunity. So when we had that idea, we started to contact companies and users that we thought would be early adopters or power users of the software to run the ideas by them and see are we on the same page with where the industry's needs are. And I think for the most part we were, but we did learn a lot on those calls. So the first thing that we learned, this came up on every single one of those calls, was that the parts in additive that are being designed and manufactured are so complex that they fall far beyond what can be simulated or even what you could generate an FEA mesh for. So we again and again saw really ridiculous geometries. I mean, things that took days to export from the CAD package, STL files that would hit the limit, the 2.1 billion triangle limit of an STL file, and need to be split into sub files. So we saw that there is a big issue with scalability of current approaches to FEA solves of these problems, and that gap between what can be designed and manufactured and what can be simulated is a very large unaddressed market, in our opinion. The next thing that we heard a lot of was that there's a lot of interest in directed energy deposition simulation. There's not many or any part scale approaches to solving those problems or large scale welding problems. So there was a lot of interest in a simulation approach that's generalizable beyond just laser powder bed fusion. And then the third thing was a confirmation of our initial thought, which is that users don't just want to predict an outcome, they want to improve an outcome. And that's optimization. So really the three big areas that we've become interested in, I'd call scalability, generalizability of the solution, and optimization. And that, excuse me, that is going to allow me to transition into what are we working on? So our product is the PanX solver. What is the PanX solver? You can see here in the middle that PanX is a collection of solver technology that opens up a bunch of new capabilities. So at its core, the technology is a highly parallelized vectorized code with an efficient FEA meshing approach. that can also do adjoint sensitivity calculations and open up a bunch of possibilities when it comes to build prep and design optimization. So what these key technologies here do is open up a whole bunch of new capabilities. So things like being able to simulate things of very large and complex scale, like big heat exchangers, being able to do part scale simulation, not just moving source simulation of directed energy deposition or large scale welding builds, being able to quickly calculate stresses without time consuming radial return, and also accurately calculate those stresses during the build. We're going to use that technology eventually as a springboard to getting into the field of fracture mechanics, which we see a lot of interest in, especially around like cracking of titanium and things like that. It's going to allow us with the adjoint sensitivity calculation to get into the field of build prep optimization. And we can also do some things around process parameter optimization. So this really is what PanX is at its core. And now I'm going to take a little bit of a deeper dive into some of these interesting technologies here. So I think, in my opinion, this may be the most interesting technology that we have, and that's our mesher. So I'm going to spend some time on this slide. So let's start looking in the middle here. So and let's forget about the mesh for now. Let's focus on what the geometry is. So it's got a lot of thick sections in it, but it also has these 50 micron thick, thin sections. So very thin sections throughout. So the question becomes, how the hell do you mesh something like that? So the most popular way to generate an FEA mesh for additive part is what I would call a uniform voxel mesh. That's not going to be feasible in this situation because the very small voxels that we need to capture this fine detail will then be forced to appear everywhere else in the part. I can't generate a mesh like that. Even if I could, there's no tool that could visualize a mesh like that. You're going to have billions of nodes. It's an impossible way to address the scalability issue. So there are ways to ease the issues that you have with a uniform voxel mesh. One way is using octree adaptive meshing. You can look up on Google Scholar. There's a lot of information about different ways to implement that for additive manufacturing process sim. And the basic idea of traditional adaptive meshing is that you populate the volume with the smallest voxels, but they're allowed to combine in groups of 8. So as you go away from the surface, the mesh coarsens. And this does ease that discretization requirement. It gets us down to, here what I've done is I've basically taken our FEA measure and tried to set settings to produce something that looks like a traditional adaptive mesh. And what that got me was 60 million nodes. And that's actually right on the cusp of what our solver can handle, but I've still listed it as impractical. And as a solution to the scalability problem, which again is trying to get our simulations up to the point that they can simulate anything that's being designed and manufactured, it isn't going to be a solution to that problem because this is actually a relatively easy part to simulate compared to what we typically are looking at. We would not classify this as a complex part. So that brings us to our meshing approach. And we refer to it as feature-aware meshing. What it's really doing is a very efficient search of the geometry before generating the mesh and essentially flagging different things. So it can say, this is a thin wall, this is a thick wall, this is a small hole, this is a big hole. And we're now completely relieved of that small voxel discretization requirement. The concept of the small voxel appearing throughout the whole volume doesn't exist anymore. It only appears where it's needed. All of the unneeded fine voxels are no longer going to have to appear in this mesh. This is a viable solution to the scalability problem. So this put our node count down to 3.4 million, and something like this can solve a mechanical solve in 1.5 hours on a desktop computer. So when we started to see these results last year, I think we were pretty excited with the potential for this. The next thing I'll touch on is that when we use that meshing approach, we're just trimming fat. I mean, there's no those voxels that aren't appearing. They didn't have any value. They were just slowing down our computation time. So we can still get very accurate results with this meshing approach. So here's an inherent strain simulation we did. So there was a calibration procedure on small test samples, as is typical in the inherent strain approach, and you can get very good agreement with experiment and very fast run times. So this is a 2 millimeter thick wall for scale. So now we take that meshing technology and we combine it with our solver architecture, which is very efficient. And this allows us to do quite large parts. So this is a heat exchanger. It's filled with very thin features. It's about 300 millimeters long. I think the STL file had around 100 million triangles, so it's not the most difficult thing that we've looked at, but it is getting into a class of problem that was not previously possible. Sorry. And this problem ended up having 76 million equations. It runs in a day on a desktop computer. It can resolve all these fine details in the heat exchanger. It can resolve the pin contact area because we're not forced to then carry that small voxel all over the part, and it can correctly identify problematic areas in the part. So there's still room for improvement on scalability. So I think that parts are going to continue to be designed that are more and more ridiculous. So I'd say scalability is still a big focus of ours. This is not, it's not something that we view as done. It's an ongoing area of research and development. But I think that these are promising results. So that's going to allow me here to pivot into the topic of generalizability of the solution. So we don't just want the solution to apply to powder bed, because we see a lot of demand for DED simulation. So the approach that we've come up with is also applicable to DED. We've done actually quite a lot of DED work, including very, very large components in the order of 6 feet long by 4 feet wide, and maybe about 100 layers of deposition. I can't share a lot of those things, but here's this is a hot wired deposited panel here, so 1.25 meters tall, and the simulation approach will work for this too. So this runs in 75 seconds on an 8-core laptop, whereas if you tried to solve this using a regular moving source approach, the computation time would explode. You'd only be able to do maybe a couple of layers of simulation. So there's good progress in the first 2 areas there of scalability and generalizability. And then the third area that I had promised I'd touch on is optimization. That's really what originally got us into this all. So our optimization problems, you can view them in the context of a problem statement. So they're set up such that you say you want to minimize some design variable, which it can be any model input. It's totally generalizable. So in this case, we're looking at support volume while not violating some constraint, which can be any model output. In this case, we're going to take a look at temperature. And I'll introduce you to this geometry here if you're not familiar with it. So this is the canonical geometry. It's designed as a part of an America Makes project many years ago. Basically, as these thin walls start to transition into thicker walls, this section gets really, really hot. And it doesn't have a clear path of conductivity down to the build plate. So it's going to get quite hot in that area. It's a very clever design for testing the types of problems we're interested in. And the PanX solver can compute adjoint sensitivities. So what the sensitivities are is it's the derivative of whatever constraint we're interested in with respect to the design variables. So in this case, the design variable is the volume fraction of the support at every point in the support structure. And what these sensitivities are telling me is that if I want to lower the temperatures in the hot sections, this is where I get the biggest bang for the buck. So it's saying we're going to take a look at adding material in these regions here, and that's what the result is going to be most sensitive to. And we can feed those sensitivities into an MMA optimizer and very efficiently run optimization problems. So this is the same problem statement. We're trying to minimize support volume while not exceeding a certain temperature. So if we have no support volume, this is turned down to 0 here essentially, we know the part gets very hot. So this is a composite image of the temperature of each layer before the next layer was deposited. These are interlayer or pre-scan temperatures. So this is the not optimized case. But since we have the sensitivities, we can efficiently optimize this problem. So what this is literally saying is I want to increase support density in this region that's going to bleed off those temperatures. And now instead of having an interlayer temperature profile that looks like this, I'll have avoided those high temperatures that violated my constraint. If you want to see what that would actually look like on the support structure, this would be just a generic support structure here. This is an optimized support structure. So it's saying add mass in this area. Another type of problem statement that we can deal with, this is a different class of optimization, which is in this case, we are looking to control the melt pool size by altering our laser power. So what we've actually computed at the part scale here is on a point-by-point basis, what do we want the laser power to be during the deposition of the part in order to get an optimized or a controlled melt pool size and optimized power profile. And we can do that on a point-by-point, a vector-by-vector, or a region-by-region basis. Another class of optimization problem here, this will probably be, all of the optimization cases I'm presenting here are in something of an alpha or a research state. So you can get a hold of it and try it, but it's not hardened like the scalable powder bed and DED stuff that I had showed earlier in the presentation. So I think this will probably be one of the first commercially available optimization abilities, which is dwell time optimization. So here I've said I don't want to exceed a certain temperature, and what I want to output is the dwell time between layers that will achieve that. So if we go with just like a constant 10-second dwell between layers, we get a lot of heating right before we link to the outer wall. But if we optimize the dwell times, we can avoid that problem. Now this was like 1200 degrees. I said I don't want to go over 150, and it's brought this entire region of the part into a uniform 150 degree interlayer temperature. And these things again run very quickly. So this is just a 24-second runtime on my laptop. So those are really each of the areas that I wanted to get into there: the scalability, the generalizability of the solution, and the optimization capabilities that we're taking a look at. If you have any interest in the software, you can feel free to reach out to us, and I'm happy to take any and all questions.
Okay, thanks, Erik. Before we go to questions from the audience, I got a few that I wrote down while you were speaking. And as far as inputs into the solver for build parameters, how do you take those in, and how can they be modified by a user?
So it depends on what scale of problem we're looking into. I mean, the basic inputs are the geometry and any information about the build plate size or heating conditions. And then the other main input for the mechanical problems that we're looking at is an applied strain. So it is an inherent strain based approach. And those applied strains get basically back calculated from experimental samples. So if you've used any other inherent strain tools, they go through the same procedure. Our calibration procedure is different than those, but the overall concept of back calculating an inherent strain from a experiment is the same.
Okay, so each user would need to make their own experimental data to feed that simulation, or is it something you provide to the customers?
Well, the goal long term is to provide as much of it as we can. So we're working with about 5 different machine vendors to pre-calibrate default parameter settings for the machines. But if you're doing something with custom parameter sets, then we just provide you the CAD file for the samples, and you can build them on your own. They're small. Okay. They're like I don't know, 10 millimeters high and 100 millimeters long. So they're designed so they can just like fit on the edge of an existing build.
Okay. And because this is a 3MF hosted webinar, I have to ask you a 3MF question. So you're currently dealing with a lot of STL files. What are limitations in using those as data transfer, and what do you hope to improve by using 3MF?
I think, the biggest issue I think with the STL is that it just has no, has no concept of connectivity, right? I mean, it's just got points and surface normals. So I think that's the most obvious step forward. And then I think longer term, I think that the 3MF should allow us to, more easily map parameter data to different regions of the part, right? I mean, some of the machine vendors we work with, they'll build a part and they might use like 4 or 5 different parameter sets on it. And if the parameters are different enough, they're going to affect the mechanical response. There needs to be an efficient way to pass that information. That isn't just like breaking the part into 5 different STLs and calibrating each one individually. So I think eventually the switch to 3MF is absolutely going to have to be made for us.
Yeah, we recently did a webinar with Additive Flow, who used the 3MF volumetric format, which is, in this case, is a bitmap stack, which represents the voxels for each layer, so they can modify the build parameters within each component and have a gradient between different parameters in different areas for different requirements. So I think that might be the way to go, hopefully, in the future, if everyone's using the same format for that. So when you were talking about optimizing the support structures, how do you communicate that data back to another tool to create those support structures? Now you have those regions identified where you need to take away more thermal energy.
Yeah, we're working with some people in the build prep space to address that, because it hasn't been addressed yet. As I said, the optimization stuff is in an alpha state, so that is the next big question of how do you how do you go from FEA voxel format to something that's consumable by a user and can be input into the machine. So
great, thanks, Erik. Now we'll take some questions from the attendees. First, we have Matthew Pelson, who's asked, he said, first up, super impressive. His question is, what is the upper limit of a big mesh? Could a heat exchanger be 10 by 10 by 10 meters structure, be meshed and simulated? And yes, he meant meters, but more interested in traditional CFD for pressure drop than a specific additive process. So I guess that means, can the meshing be used for other CFD processes, etc.?
That's a good question. So the meshing could be used for other applications beyond additive. We haven't really, we've discussed branching into binder jetting, but I don't think we've ever talked about the CFD application. I think Pan's on the call. He might have more to add on that point.
Yeah, I mean, hi everybody. Thanks for this opportunity. So, yeah, the meshing could be used for any other application, either FEA or CFD. The thing to note is that the mesh is not uniform voxel, so there's adaptivity, octree adaptivity, and there appears to be what's called hanging nodes. They're not really hanging, they're constraints associated with those nodes. So whatever simulation software it's going to be used. After that, it's has to have an efficient way of handling constraint equations, and this kind of problems, they usually about almost like a third or maybe a quarter of the degrees of freedom in the model are constrained. So it has to be a very efficient approach. So in our approach, we use condensation. If you have something less efficient, like a Lagrange multiplier approach, is not going to work. So that's the main constraint. As far as the meter by meter by meter, I knew that people would try to find the limits of this code too. The limits of the code is now there's 2 branches in the code. One is running on a single node, and then running MPI on a cluster. And the bigger the model, the more RAM you need to run it. We use the MKL solver was the part D, so now they call it sparse equation solver. The issue that we're facing is that Intel has a bug on the MKL, the distributed version, the MPI version has a bug. When you exceed, when the number of non-zeros in the matrix gets close to the 32-bit limit, 2.1 something billion equations, no, I'm sorry, non-zeros, the solver crashes. I reported this to Intel about a year ago, And they promise they're going to have a fix for this in 23.1 version, but they've been silent lately, so I doubt that's going to happen. So if you got anybody at Intel, let them know. So that's the limit now. So then the issue that you have is then the single node solver has no issues. It can go beyond that limit. So then currently our limitation is that we can run on a single node what memory you have. And it turns out to be you can run about reasonable time, about 200 million equations. I am working on methods that would allow the solver to, as these models go into higher and higher layers, what happens is you have to solve more and more equations. I hope to have a method where the simulation, instead of not only adding more equations, can actually drop equations from the lower layers, but they're still in development. So I'm expecting people will try to find something that is even beyond the limits of the current solution, and I'm working on something that can do a 10 meter by 10 meter doing 10 micron depositions, 100 micron depositions. So it's not available yet, but it should come something later this year.
That's okay though, Pan. Imagine how long that would take to print 10 meters by 10 meters at 50 micron.
Well,
Forever.
for me, I'm trying to be ready for, I've been in this business for too long. And usually what happens is you give someone a tool in the beginning, oh my God, I'm gonna solve all my problems. And then 2 weeks later say, okay, I need more. So I'm anticipating that. So.
Okay, another question we have around features are, if you could clarify what features are currently available in the software as they're interested in support optimization based on a constraint.
So commercially available and hardened, we have users for the solving forward problems for the large scale powder bed, as well as solving forward problems for some of the DED stuff that I had shown. All of the optimization examples we would classify as being in an alpha state. They come along with the commercial product as an alpha right now, so you can get a hold of those features, but the caveat is that they've been tested and hardened far less than the other features of the tools. If somebody has an example of a support optimization problem they're working on, please follow up with us and we can get a little research project going and take a look at it.
Okay, thanks, Erik. The next question is, do you consider any nonlinear material behavior, for example, temperature dependent material behavior or elastic plastic material, etc.?
That's a good question. So the at the part scale, it's inherent strain based, so it's being solved as an elastic problem. So that the applied strain is being input based on the sample. We have had this just came up maybe 2 weeks ago, a request for large deformation simulations, right? Thin wall buckling, those types of nonlinearities. That work right now, or there's a feature for that, right? I don't know if it.
First of all,
what happens if I turn it on?
No, I actually like to turn it off intentionally because I had no time to verify. I have a draft solution, but I have not released it commercially yet. I need to do more testing. I mean, the nonlinear deformation, it's a relatively straightforward thing. I think the question was regarding materials. We do offer full elastoplastic moving source material response where you can run radial return algorithm. But as Erik alluded into his primary slide, there is a new constitutive model says that the part scale simulation, although it is primarily driven as inherent strain, it does include a plasticity correction and the relaxation correction if the material requires that. So if you do heat treatment, say I build up to that 50 layers and they want to heat treat the part and relax it, there's actually even the commercial release has this feature in. And then there is option to do things like polymers where they have a significant creep through the process. So but the objective is to do those efficiently. So we do not run by intention radial return for the part scale, but we do have a plasticity correction that gives good stress predictions based on trying to emulate the plasticity.
Cool, thanks, Pan. Well, we've come to our 30 minutes and people are starting to drop off, so we'll close this out. How can they get in touch with you if they're interested in learning more about Pan optimization?
Info at PanOptimization.com.
Yeah,
info@panoptimization.com.
Yeah, or you can check out the website, which is, of course, PanOptimization.com.
That makes sense. Okay. Well, thank you both for presenting today. I really appreciate it. And thank you for joining.
Thanks for organizing, Dawn. Really appreciate it.
Thanks, Don.
Oh, yeah. And there's a